Okay, this is section 2.2, the derivative as a function. So before we were looking at the derivative of a function at a certain value. Now we're going to consider the derivative of a function as a function in its own right. So we'll define the derivative of f, and we'll denote it as this f prime. This is the notation that's commonly used. F prime of x is how it's read. And it's defined as the limit as h approaches 0 of this quotient f of x plus h minus f of x over h. So now, as before we had a's involved, now there's no a's, it's x, so the variable x, not a constant a. So here's an example. We have the function defined, f of x is x to the third minus x, and so we're going to find the derivative f prime of x. So write it out as the definition. F prime of x is the limit as h approaches 0 of, I'll put the definition first, f of x plus h minus f of x all over h. Now I'm going to expand out this numerator. I'm going to plug in, instead of f of x plus h, I'm going to put x plus h in place of the x's. So this is the limit as h goes to 0. And we've got x plus h to the third minus x plus h, and then we're going to be subtracting x to the third minus x. All of this over h. Now, of course, we have to expand out all of these little pieces. So we're going to get x to the third plus 3x squared h plus 3hx squared plus h to the third. That's how you expand out this x plus h to the third. And then we're going to subtract x, subtract h, and then we've got minus x to the third, and then the minus will be plus an x over h. Now I'm going to cancel out a few things that do cancel. So for example, the x to the third and this x to the third are gone. And we've got this minus x and this plus x, those are gone. Everything else stays, but I'm going to factor out the h's. So this is limit as h approaches 0. Okay, so the first term, I'm going to take the h out. Every term has an h. So we've got 3x squared plus 3xh plus h squared minus 1. All of this stuff is what's left when you factor out the h, and then you have this h. So those are going to cancel. Now when h goes to 0, then these two terms are going to be 0, and what we're left with is 3x squared minus 1. This here is the derivative of x to the third minus x. Here's a graph of f of x. This is the graph of x to the third minus x. In here I've overlaid the graph of f prime, 3x squared minus 1. As another example, let's take the square root function and find its derivative. Okay, so what we want to write again, so the definition, f prime of x is the limit as h goes to 0 of the let's write it out. Square root of x plus h minus the square root of x over h. To evaluate this one, what we're going to do is we're going to multiply both numerator and denominator by the conjugate, which is square root of x plus h plus the square root of x. That's going to go on top, and it's going to go on bottom. Okay, so then we're going to, up top, the limit as h goes to 0. When we multiply this binomial with its conjugate, we get the first term squared and the last term squared. So it's going to be x plus h minus x. That's what we're going to get up top. Down below, we'll have h times this other business. Now, I'm not going to try to do anything funny with that. I'm just going to leave it as is because it's going to simplify a little bit more in a little bit. Because, okay, so what do you see? You have x plus h and then you have minus x. So actually the x's are gone. And so what we get is limit as h goes to 0. And I'm going to take the h over h out of this, and then what I'm left with is a 1 up top, and I'm left with root of x plus h plus root x down below. The h's can go, and now I can take my h to 0 without a problem, right? So what we're left with is 1 over root x plus root x. That's 1 over 2 root x. That's the derivative of the square root of x, 1 over 2 times the square root of x. And as you know, what is the domain is going to be x has to be strictly greater than 0, because although for the original function the domain included 0, because you can take a square root of 0, you can't put the square root of 0 in the denominator and get away with it. That's a no-no. So the derivative function is only defined for x being strictly greater than 0. Here's another example we'll look at. F of x equals 1 minus x over 2 plus x. So let's find its derivative. F prime of x is the limit as x goes to 0 of, now I'm going to be a little bit more careful right now. I'm going to just write the derivative definition first. I'm not going to skip that because this is a little bit funkier. F of x all over h. Now I'm going to take the 1 over h out to the front. And you can see I made a little mistake over there. This is the limit as h goes to 0, not x goes to 0. So let's fix that. Okay, h goes to 0. I'm going to put 1 over h times, now I'm going to put in 1 minus x plus h over 2 plus x plus h. That's my first fraction, minus 1 minus x over 2 plus x. You see, I'm putting the numerator over there because I don't like having fractions on top of fractions. I'll have it as 1 over h times this difference. I'm going to simplify things by trying to work things out a little bit. The limit as h goes to 0 of 1 over h times, let's see, we have 1 minus x, it would be minus h, 1 minus x minus h over 2 plus x plus h. All right, minus, well, that's not going to change. 1 minus x over 2 plus x. I'm going to try to get common denominators. In fact, let's move things over a little bit. And we'll see the common denominator I get is going to be by taking this first fraction and multiplying it by 2 plus x over 2 plus x. And the second fraction, I'm going to multiply it by 2 plus x plus h over 2 plus x plus h. I have to take the time and work this out and just trust that some things are going to cancel and I'm going to get some h factor on the numerator. That's really what happens for these most of the time. Okay, so let's multiply this 2 plus h. So we're going to have 2 times this first, so this is 2 minus 2x minus 2h, and then it's going to be plus x minus x squared minus hx. That's what I get up top. Okay, that's this first fraction. I'll do the second part. It's going to be minus, I'm going to multiply it out. 1 times 2 plus x plus h is going to be 2 plus x plus h. Nothing special happens there. Minus x times each of those terms. We'll have minus 2x. We'll have minus x squared. And then we're going to have minus hx. Okay. Down below, when I multiply this, first I'm going to do the 2 times this 2 plus x plus h. So we're going to have 4 plus 2x plus 2h. And then I'm going to have the x times each term. So plus 2x plus x squared plus h. All right. I'm going to have to make sure things are going to cancel. So I'm going to write it out a little bit. I'm going to collect whatever I can. I'm going to still hope that I get some stuff canceling. So what do I have up top? So so far in the first term, or the first group of things. Okay, so we have minus x squared. We have, so that's the x squared. That's this one here. We've got x. We have minus 2x and we have plus x. So that's minus x. Okay, that's those two are done. Then we've got minus hx, and then we have minus 2h, and we have a plus 2. Okay, so that's all of those little bits. Then we're going to be subtracting each of these. We have minus 2, we have minus x, minus h, we have the plus 2x. So actually, let's change that to a plus x, because it's minus a minus 2x plus an x. All right, minus, okay. Then we have the plus x squared, because that's minus a minus. We have plus hx. So what do we have that's canceling? Well, let's do the denominator first. We have x squared. That's fine. 2x plus 2x. We're going to have plus a 4x. And let's see what we're going to also have a plus hx, and then we're going to have, let's see, we have the plus 2h and we have plus a 4. Okay, things that cancel, we have the minus x squared and the plus x squared. We have the minus x and we have the plus x. We have a plus 2 and a minus 2. And yes, everything that doesn't have h is going. So that's good. All right. Now, if I was to factor out an h from the numerator, okay, I'm going to get what's left over is we have, actually, now that I notice it, we've got a minus hx and the plus hx also canceled. So what we had left was minus 3h, right? Minus 3h, and then the minus 3h, only the minus 3 remains. Down below, x squared plus 4x plus hx plus 2h plus 4. And now we're going to get the limit as h goes to 0. All of the h terms are going to be gone. And so we're going to have minus 3 over x squared plus 4x plus 4. I realize after doing this that actually I could have not distributed out the denominator, because I would have just gotten 2 plus x squared after h goes to 0. So we could have had a little less pain. It would be x plus 2 squared in the denominator. But either way, we got our derivative. Here, I just want to note a few other notation you'll see here and there for the derivative of x. Now, because we sometimes say that y equals f of x, that's going to give us this y prime as a notation. Now, sometimes we write dy over dx, which is like saying what's the change in y for a instantaneous like change of x per like change of x. The d over dx that we see here again, this is what's known as a differentiation operator. And then this capital D f of x, or this capital D with a subscript x, this is also a differentiation operator. It's just saying the derivative of f of x. So that when we see dy over dx, you should think this is also a limit. This is a limit. The change in y, how does y change? The change in y divided by a change in x when the change in x approaches 0. And that's what we've been doing this whole time. The change in x is like your h. And if we wanted to note the derivative of the function when x equals a, you can sometimes, of course, we were writing f prime at a, but you could also write dy over dx, and then this line, x equals a. This is another way of denoting. You take the derivative and then you evaluate it at the value x equals a. We'll say a function is differentiable at a if f prime of a exists. And we'll say a function is differentiable everywhere on some open interval a to b, or we might have from a to infinity, or negative infinity to a, or from negative infinity to positive infinity. It would mean that the function is differentiable at any number you would choose that lies on that interval. A theorem that we have that is if the function f is differentiable at a, that means that the function is continuous at a. But it should be pointed out, it doesn't mean that if it's continuous, it's always differentiable. And there's plenty of cases where that is not true. It's if differentiability implies continuity, okay? For example, the absolute value function is continuous everywhere, but it's not differentiable at 0 because the function has, as you approach this from two different directions, the slope of the line is +1 on the left, on the right, sorry, and it's negative on the right. So at that corner, it has no defined. It's different from both sides, so it's not differentiable at that point. In fact, we all know already corners, points, things like that, those are points where functions are not differentiable. Since f prime is a function, it may be differentiable, like it may be a differentiable function, so we could take its derivative. Its derivative would be denoted f prime prime. We don't actually draw the parentheses. Usually we just say f with two little ticks. F double prime, we usually say. And that's known as the second derivative of f. Other notation you might see, this d over dx, this differentiable operator applied to dy over dx, we write it with as d squared y over dx squared. This is notation that's very common to see. So for example, let's find the second derivative of x to the third minus x. We already know that f prime of x is 3x squared minus 1, so let's find f double prime of x. That's going to be the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. Well, we're going to just put in x plus h into that 3x squared minus 1. It's the limit at h goes to 0. We have 3x plus h squared minus 1 minus 3x squared minus 1, right? Minus that all over h. We're going to expand and we're going to simplify. This is the limit as h goes to 0. We have, let's see, it will be 3 times x plus h. That will be 3x squared, and then it will be 2hx, but that's times 3, so it's going to be plus 6hx, and then plus h squared, but that's going to be times 3, so it's plus 3h squared, right, minus 1, but that's minus a minus, so it's going to actually be a plus 3x squared, and then plus that 1 all over h. Of course, we have some nice canceling that happens. I don't know why I made that positive. It should be negative. It's minus 3x squared. Okay, and that's what cancels. So let's do this in red. This cancels with that, and this cancels with that. And then let's write this out. Limit as h goes to 0. I'll pull the h out from the numerator and the denominator. What we're left with is 6x plus 3h. And as h goes to 0, this first part, well, this is going to cancel, and then this is going to go to 0. So all we're left with in the end is just this 6x. That's the second derivative. Okay, cool. So let's, as a couple other notes, so in physics, if we're like describing an object's position as a function f of x, we would interpret f prime of x as the velocity of that object at any time x. And the second derivative, f double prime, would be interpreted as the acceleration of that. That's how is the velocity changing at any given point in time. If we wanted to denote the third derivative of a function, we would do 3 ticks, but for the fourth derivative and any higher derivative, if we ever would need that, you would denote it like this. We would put a little 4 in parentheses up in the superscript, so we don't get overwhelmed by little tick marks. So that notation is commonly used for higher derivatives than the third derivative. So as an example, let's find the third and the fourth derivative of f of x equals x to the third minus x. Because we already have the first derivative was 3x squared minus 1. We had the second derivative. We found that. That was 6x. So let's figure out what to do with the third. Well, triple prime of x is going to be the limit as h goes to 0, right? I'm going to write actually, I'm going to put, it's the function f of x plus h, which is going to be 6 times x plus h minus f of x, 6x, all over h. This is a little simpler to do because nothing is squared. And I'm just going to distribute this 6. We have 6x plus 6h minus the 6x over h. And the 6x's are going to be gone. And so what we get, then this is the limit as h goes to 0 of h over h times 6. And so the h's are gone, so the limit is going to just be 6. That's my derivative. Now what's the fourth derivative? The fourth derivative, of x, that's going to be the limit as h goes to 0 of, what's the third derivative evaluated at x plus h? That's just going to be 6, which is to say, it doesn't matter, there's no x's involved. That's going to be 6, it's constant. So it's 6 is, this is f triple prime x plus h, and then minus just 6, which is f triple prime at x, right? There's no x's in the function, so it doesn't even matter. 6 minus 6 is 0, so this is the limit as h goes to 0 of 0 over h. And it doesn't matter what value h is, this is just 0 always. For any value of h you would pick, this is always going to be equal to 0. So that's the limit, it's 0. All right, well that's the derivative of a function, or the derivative, I should say, as a function, treated as a function, and we're going to be treating derivatives as functions for the remainder of this course. All right, bye-bye.